Happy to have Zoe give lecture two in her lecture series. So take it away.
All right, thanks. So thanks everyone for being here online. Please do write questions in the chat if you have them, or obviously unmute yourself. So yesterday I wrote things on the board, and I got a little bit behind schedule as well. And so now I have very quickly this morning put my notes into Beamer form. So we've got slides, which obviously means I can go a bit faster, but there may be typos because I've just done it this morning. So apologies in advance for that. So just a little recap, okay, of where we ended up yesterday, okay, was this idea to begin with the cosmological principle that we're going to model the cosmos, the universe, as a Lorentzian manifold. Okay, so a manifold M of 1 + 3 dimensions equipped with a Lorentzian metric. And we saw that the assumption of isotropy at every point in space, okay, would imply also homogeneity, and this would restrict the class of spacetimes that we have to consider. So in particular, we were able to reduce our metric to the FLRW metric, okay, which looked like the following here in spherical symmetry. But the key feature that we had here was that we had a scale factor A of t, and this was giving us this local expansion, okay, or kind of expansion between fundamental observers, okay, are being scaled by this factor A of t. What else we did, just to remind you, we talked about the co-moving coordinates. Okay, so these are, for example, here of r and theta and phi. Okay, you might call them x1, x2, x3. But these are co-moving because they're moving with the expanding grid. Okay, and then we also just have the physical coordinates, which is just when you rescale these things by the expansion factor A of t. And we also saw one kind of parameter, what's called a parameter, that's just kind of the name that it has in cosmology, is this Hubble parameter. And it's just defined by a dot over a. Okay, so the time derivative, the scale factor over a, and it's just a combination that's going to appear lots today in the equations of motion and things like this. All right, so this was what we saw yesterday with the metric, and then Einstein equations relate geometry, okay, to matter. And so we also saw that isotropy and homogeneity restrict the type of matter that you can have. And in particular, we saw that the matter should take the stress energy tensor, okay, on the right-hand side of the Einstein equations, should take this kind of very simplified form on the right here. Okay, and it ends up that this is actually the stress energy tensor for a perfect fluid. Okay, so an idealized fluid, which is just described by its energy density, its pressure, and its force velocity, capital U, okay, or U, whatever you might want to call it. And what else we saw was we saw that conservation laws, okay, for the Einstein equations imply an equation of motion for this perfect fluid. And we get back something that you'd also have in a non-relativistic theory. We get back a continuity equation here. Okay, and you'll see already that actually we've got here a dot over a. We've got the Hubble parameter appearing already. Okay, appearing in this equation. So here we're still working in isotropy and homogeneity. Okay, so that's why here really everything just depends on time. And we can solve this continuity equation here, okay, provided that we can remove one of the variables. So in particular, we can remove the pressure, okay, if we impose an equation of state that you do in fluid dynamics, right, to be able to close your system. So here we can find a relationship between the pressure and the energy density rho. Now, I'll just mention there's kind of lots of different equations of state that people do take. In astrophysics, people often take what's called a polytropic equation of state. Okay, so that's where your pressure is related to some power of the energy density. But in cosmology, okay, which is more large scale structures, it is standard to take what's called the linear barotropic equation of state. Okay, so barotropic just means that the pressure is just a function of the energy density, and linear here because we've just got this number k. All right, so you'll often see in the literature, you often see k Might also be written as cs squared. Okay, so you can identify it as the square of the speed of the sound waves. Okay, but I prefer just to write it as k. And so if you have this relationship, right, then we can substitute this into the continuity equation and solve, okay? And in particular, we see that the energy density should dilute, which is, of course, exactly what you'd expect, right? You've got your space-time expanding, you're not creating matter from nothing, so you expect your energy density to be diluting at some particular rate. And so just trying to move that over there. The kind of two really key cases in cosmology, okay, are modeling matter which has no pressure, okay, very, very low pressure, and this is called dust, okay, or matter, cold dark matter as well is included in this, okay, and we also might want to model radiation, okay, and some particular photons, such as the photons that were emitted in the cosmic microwave background. Okay, and in that case, you actually take P to be 1/3 of rho, so K is equal to 1/3. Okay, and so we see here the dilution rate does depend on the type of fluid that you have. Okay, so we've now got this continuity equation, right, which is telling us how rho relates to the scale factor A, but we still need to find an equation for A, right? How does this scale factor evolve? And so for this, we are just going to use the Einstein equations, okay, to determine the evolution of this scale factor. So Einstein equations are, of course, Ricci minus 1/2 Rg is equal to stress energy tensor, which we've now determined. So what we need to do is we need to compute the Ricci tensor for this FLRW metric. Okay, and it's just a straightforward computation. Okay, and there's only a lot of components are 0. Okay, the only non-vanishing components are the one that I've written here. Okay, so the R00 component and also here the Rij component. All right, and so note actually that what we get here in this second identity here, right, we're showing that the Ricci tensor on the 3 manifold Rij, right, is proportional to Gij, okay, which is exactly what you would expect given our assumption of isotropy at every point. Okay, and just here the constant of proportionality, which is not really a constant here, right? It's something that depends on time. Okay, so if we take the Einstein equation and we evaluate the 0, 0 component and we evaluate the Ij component, okay, on both sides of these equations, we then obtain the following two equations here. Okay, put a comma there so you can see the distinction. So just to unpack these a little bit, so you notice here on the left, I've got A dot over A, so I've got the Hubble parameter squared. I've got here something involving the sectional curvature of the 3 manifold K. On the right-hand side, I may have a cosmological constant, okay, because that was actually, that's also in cosmology, it's also something that we want to put in. Okay, so I may have a cosmological constant appearing here. And then we also have some energy density. And so you should really interpret this rho here as being a sum over lots of different energy densities of different fluids, okay? Because our universe is filled with lots of different fluids, so in particular matter, cold dark matter, baryonic matter, as well as things like radiation coming from photons and radiation coming from neutrinos, which are basically massless. Okay, so this is kind of, this rho here is a sum over lots of different rhos. And the other equation that we get is the following one here. Okay, so now this is telling us something about a double dot. Okay, and we see here that we've got, on the right-hand side, we now pick up something that depends on both rho and on P, okay, and also on the pressure. So if we just kind of look, actually, really the second, okay, so the two equations are basically equivalent, provided I think A dot times A is non-zero. So if we just focus on this second equation a little bit, we can see a few things. So, for example, if lambda is positive, right, if lambda is a positive number, then that's going to be causing A double dot to be positive. okay, which is, as you imagine, it's increasing acceleration, so it's increasing expansion. Okay, so positive cosmological constant is something that's driving expansion. We also see that because of this minus sign here, we actually get something different when we have, for example, pressure. Okay, so um, here, for example, if you have some pressure, if you have increasing pressure in particular, okay, then we see that because of the minus sign, that pressure is working against the acceleration. Okay, it's decreasing a double dot. Okay, and so this decelerates the expansion. Okay. Um, and of course, that's only something that will be the case if we're outside of radiation. Okay, so that's something else to note there. So these equations here, these equations, that one there and that one there, these are called the Friedmann equations. And you can do, there's a whole, I think, frankly, beautiful world of dynamical systems analysis on these equations. Okay, so finding steady state solutions and analyzing, yeah, the properties of these dynamical systems. We are just going to look at a couple of explicit solutions to these ODEs. Okay, so let me just give you a quick example of that. So if we take k is equal to 0, so in particular, I'm thinking about my manifold being R3 or T3. Okay, so no sectional curvature. And just for the moment, let's suppose we only have one type of fluid. Okay, so I've just got one type of fluid, k is equal to 0. And so we can solve the equations. Okay, we can solve it explicitly. So let me just show you here. In the case of dust, okay, when the pressure vanishes, well, I can solve the continuity equation. I can integrate that up, and I see that rho should go like a constant times the scale factor to the -3. Okay, that's actually something we did yesterday as well. But now I can also determine how A behaves because I can go to my Friedmann equation, the first one, for example, and I now get a differential equation where here I've got a dot, okay, and I can integrate this up, and I see that actually here now A of t is going to go like t to the 2/3, right? So this is going to be an explicit solution to the Einstein-Euler equations filled with the dust fluid. And it's, it's such an important solution, right? It really does have a name here. It's called the Einstein de Sitter cosmology. Okay, so we have here, we know what can we say from this expansion factor A of t is equal to t to the 2/3, right? We see that the universe is expanding, okay, because obviously t is increasing, so it is expanding, but it is doing so at an ever decreasing rate, right? Because if you work out what h of t is for this solution, right, you're going to get something like 2/3 times t. Okay, so the rate of expansion is decelerating. Okay, so that's one explicit solution that we can construct. Another explicit solution that we can construct is the
Zoe,
radius.
could I ask a question?
Yeah, of
Oh yeah.
course.
So there was the other equation with the two second derivatives of A. Is that one follows from these ones or?
Yeah, exactly. Yeah. So these are, you can show that these are equivalent provided that kind of A dot times A is non-zero.
Got it.
Yeah,
Okay.
that's it. Yeah. So we just need to
Thanks.
show one of them. Yeah, thanks. But I must say, I do think it's good actually to kind of this second equation, it's a nice interpretation to think here that the pressure is, if you have like increasing pressure here, is decreasing your acceleration. Whereas if lambda is positive, that's increasing your acceleration. So I think as an equation, that one's quite nice for that intuition. Okay, so when we go to radiation, okay, so now my pressure is 1/3 times rho. You can do the same thing. Okay, we can solve our continuity equation and we can solve the Friedmann equation. Okay, so again, two things that we can solve. And I'm just telling you here that this is the solution that we will get. Okay, where you get your scale factor is going to grow like t to the half. Okay, and the energy density here, rho, is going to scale a bit slower, a to the -4, but actually ends up decaying at the same rate, t to the -2. Okay, so one thing to note here with these two solutions, okay, is we see that when we have a radiation dominated solution, okay, so when the radiation fluid is really the dominant part, the expansion is slower. Okay, the expansion is only like t to the half. And that's really, you can kind of view this as saying that it's because of the pressure, the additional pressure that's coming from the radiation, which is decreasing that, how much A can grow, how quickly A grows. Okay, whereas here we don't have any pressure, and so that's why we're able to get a slightly quicker expansion rate of t to the 2/3. Okay. So this is the case when we have two separate components, okay? But of course, actually in physics, we want to have lots of these components, right? And we're trying to understand how they evolve together. And so maybe just to tell you some facts, right, is that our very early universe, when the cosmic microwave background was emitted, okay, is expected to be what we call radiation dominated. Okay, so in the very early universe, we really expect the dominant component to be coming from the energy density of radiation. Okay, so we've just seen that the scale factor grows like t to the half in that case. And we've now seen that the energy density of the radiation decays like 1 over t squared. Now, what you can do, okay, is you can actually take this scale factor here, A of t goes like t to the half, and you can put this in your continuity equation, okay, and you can see how would the matter decay. All right, now if you do that, if you put that into your continuity equation and you solve it, you see that the energy density of matter actually decays like 1 over t to the 3/2. Okay, so in cosmology, what we view this, obviously, this is very heuristic, right? But it's telling us that this is an unstable epoch because it's saying that even though at C and B we had lots of radiation around, very quickly, or kind of what happens is that the radiation actually decays faster, okay, than the matter because the matter decays slower. So you get a transition, and so you're going to get actually that the radiation is going to decay sufficiently fast, and the matter is going to kind of persist. And so this epoch is unstable, okay, because we then are going to move to what's called the later epoch, which is matter dominated. Okay, so that's the other solution that we solved just before. So in the matter dominated epoch, the expansion rate grows like t to the 2/3. Okay, and in this case, you can then again solve the continuity equation assuming this scale factor growth rate. And you'll see here that the energy density of matter, of dust, okay, decays like t squared, while the energy density of radiation decays like t to the 8 over 3. Okay, and so this is more stable because, you know, as we see here, the radiation is decaying faster. Okay, so just to give a quick picture, okay,
Uh,
of, yeah, go ahead.
sorry.
Yeah.
Sorry. So is that something you can like can you find can you prove that that happens? Like, is that easy to do or
Um, you can you can construct a multi, you can actually explicitly construct a multi-fluid solution. So like here I've taken them separately and then I've kind of argued
yeah.
heuristically by putting them together, but you could also do an explicit one of the two together and then you would get
And it's stable? Like,
right, okay, sorry. When I say stable, I'm really just saying at this level. No, not proper stability here.
all right, but there are solutions which connect the
There are
radiation
there are solutions that connect the two.
to
Yeah.
and all right, so
Yeah.
but
Yeah, but
okay.
certainly like in
But
terms of analyzing like stability, let's say in the nonlinear PDE sense, no,
no,
that's
I don't mean in the PD sense. I mean,
okay.
fine sticking with the ODE.
Okay. Yeah,
Yeah, I'm
you
wondering.
can exactly. You can construct a solution that will interpolate between the two. Yeah.
All right. Thanks.
Um, so I just wanted to have a brief word again. I know it's a bit of physics, but just to, outline what is our best model, okay, in what cosmologists do. So the idea is that we have, okay, something happened around the Big Bang, not really sure in classical physics how we can analyze that, but we've talked lots about the emission of the cosmic microwave background, okay, which was our kind of initial conditions of isotropy and homogeneity. And the idea is that in the very early universe, okay, to begin with, we had a radiation dominated epoch, okay, which we've seen here should grow roughly like t to the half. And then after this epoch, there should be another epoch where the scale factor grows like t to the 2/3, okay, this matter dominated epoch. And then experiments and observations and things like this, or sorry, not experiments, observations have shown that it was only kind of in the last 5 billion years of our universe's existence that actually the scale factor started to grow at this exponential rate, okay, e to the ht, or e to the, sorry, let me eventually try and write something useful, e to the kind of lambda t, roughly speaking, maybe up to a square root of lambda, okay? And so it's the scale factor in the universe has changed, okay, and so different components have dominated at different points in time, and what we'd like to do, okay, is we'd like to understand how have galaxies and very large structures, how have they formed, okay, and what we see really is that these things are not forming in later epochs, okay, they're really going to be forming in these earlier epochs, okay, and it's, let's say, trying to understand some mechanisms for that structure formation. Okay, so in particular in the radiation epoch and in the matter-dominated epoch. So I promised you we'd talk about some PDEs, so that's what I'm now going to get cracking on. And we've seen so far, right, we've seen that the fact that we have cosmological solutions mean we have this expansion, and that's something that leads to dilution. And what we're going to see in the PDE world is that dilution term is really going to correspond to damping terms in our PDEs. Okay, now what I'd like to show to you here is two kind of dynamical effects that are studied in cosmology. Or actually, let me phrase it differently. So I'm going to outline to you a heuristic argument, which is called the Jeans instability. And this is one of the main models that's used in cosmology to understand the behavior of structures forming. Okay, so it's a gravitational effect, and the idea is that if we take C and B, okay, it has very small anisotropies, so it's got very small variations in energy density, and these small variations lead to a bit more clumping, which leads to a bit more clumping, and the idea is that that clumping grows and grows to the point where at later times we see structures forming. Okay, but in terms of rigorous PDE dynamics, there is essentially nothing that is understood for the Jeans instability, okay, rigorously. And I think one thing that's quite interesting in this area of research, okay, is what we obviously study a bit more in PDEs, which is the idea of fluid shocks forming, okay, which we might think of as a more local kind of structure formation happening. And it's, I guess that it's quite amazing, but there's really not as much kind of the interaction of these two and kind of how they're related is really not as well understood. Okay, so hopefully I can just tell you a little bit about these things, and you'll get a bit of an idea of what we know and what we don't know. So let me talk a bit about the Jeans instability now. And oh yeah, actually, I probably just had a quick slide here to remind us about damping terms in PDEs. So we've had the lectures by John Anderson, talking about dispersion and decay for solutions to nonlinear wave equations. Okay, so hopefully by now we're all happy that solutions to the linear wave equation in 3+1 dimensions, okay, are decaying in time. And while solutions to this first equation can decay in time, okay, and go on their merry way, we can arrange to have certain nonlinearities that will produce very different dynamics. Okay, so in particular here, you can obviously on the right-hand side have lots of different nonlinear terms, maybe even depending on derivatives and things like this. But it's quite simple to cook up certain nonlinearities, which will actually give us finite time blowup. Okay, so the example here, I've got some power law nonlinearity here, P, okay, and for some particular range of parameter P here, okay, you can get global existence, small data global existence, or you can get finite time blow up, okay? And that's, all well and good, but how does damping arise when we're talking about wave equations? Okay, damping terms will actually drastically affect the dynamics. And so in particular here, what does a damping term look like? At least for me, I mean it in the context of adding a term which is like plus some parameter d, okay, times phi t. And why does it lead to damping? Okay, at the very rough heuristic level, we can just do an energy estimate, okay, which I know in the other course by John, he was doing lots of energy estimates like this. So the most basic one would just be saying take the time derivative of the energy functional, which is formed by the phi t derivative squared and the space derivative squared. Okay, now if you've got a solution to the linear wave equation, right, if you don't have any damping, when we know that this energy is conserved, whereas if we have a solution to this damped wave equation, then what do we get? We get a term here on the right-hand side, which is minus d times an integral of phi t squared. Okay, now this obviously doesn't tell you everything because we've only got phi t squared. We don't have the spatial derivatives. Okay, so we haven't recovered the full energy. Okay, but I hope at least heuristically you see that this integrand here is non-negative. We're going to have minus times d. D will always be a positive constant. Okay, and so this is a term here that is driving a decrease in the energy. Okay, so we would expect some kind of damping in our dynamics. Okay, and this has actually been studied. The competition between damping and blow up has actually been very well studied. For example, here in the context of this scalar wave equation. Okay, so I just say here many works. I don't have the time to go through them all, but here what you'll see is we've got both a damping term, okay, which I guess here involves phi t to some power m, whereas on the right hand side we have this blow up nonlinearity. Okay, and so it has actually been very well studied, the competition between these two effects. Okay, so for particular values of m and for p and for d, you can set things up so that we get global solutions or we get finite time blow up. Okay. So keeping this in mind, in particular, keeping this idea of what this damping term looks like, we can now talk about the Jeans instability. Okay, so to get us going, I just want to recall quickly the compressible Euler equations, okay, which are written as follows here. Okay, and I guess I just wanted to make one very quick comment, but on shock formation for these equations. But yeah, maybe actually I'd talk about shock formation at the end. So let's just recall that we have these compressible Euler equations. Now here we have, sorry, I just think just because I wrote the slides this morning. So here I just have an equation for rho and I have an equation for u for the velocity. And what we'd like to do in cosmology, okay, is study some fluid on one of our cosmological spaces. Now, everything I've said to you so far has been looking at the Einstein equations coupled to a relativistic fluid. But in various situations, that's almost overkill. Okay, we know that kind of relativistic gravitation is very well approximated by Newtonian gravity. Okay, and so for a very long time, and even still in cosmology, people actually, instead of studying, let's say, Einstein Euler, they might just look at Newton plus Euler. Okay, and so for that reason here, we can just look at a non-relativistic fluid, okay, compressible Euler equations. Now, as I had here, okay, so I said here we know that these solutions lead to shock formation. Okay, this has been very well studied in PDEs, okay, for large classes of data and things like this. And I guess very heuristically, these shocks are really coming from the Burgers term, okay, which is like U grad U. What we're going to see now in cosmology, which I actually really think is fundamentally why these mechanisms are quite different. In cosmology, people study a mechanism called the Jeans instability. And what we'll see is actually in this mechanism, they neglect, or it's a linearized argument. Okay, so they're going to neglect all higher order terms in their equations of motion. And so in particular, they're actually not going to take the Burgers term. They're going to set that to 0. Okay. But what we're going to do is we're going to add in the effect of gravity, okay, and that's actually going to nevertheless lead to some kind of shock formation in the sense that a certain part of the energy density is going to increase very quickly in time. Okay, but somehow just quite amazing in cosmology that just because this genes mechanism, it's going to involve setting all higher order terms in our PDEs to zero. And so actually what we would think is the key thing that drives shock formation is not actually something that is relevant in this mechanism. Okay, so let me explain a bit more what I mean by this. So if we'd like to add in gravity, okay, then we're going to be looking at Euler-Poisson. So here I've kept my continuity equation, I've kept my momentum equation, and I've now added in a potential term, okay, coming from the gravitational potential energy, and we've got the Poisson equation here. And this system of equations, okay, admits a homogeneous background solution, which basically means that rho bar, p bar, phi bar can all be constants, okay, so they don't depend on space and time, and u would be zero. Okay, so this would be our background solution, and natural question to ask is what happens to perturbations around this background solution? Okay, can we study them? So what we can do is we can linearize the equations, okay, which means that I'm setting all, as I said, higher order perturbations to zero. Okay, I'm just kind of looking at order epsilon terms in my equation of motion and order 1 terms. Okay, so if we take these equations, we can linearize them. And so what I've introduced here now is just some notation check. Okay, so rho check, which is supposed to be the variation of the energy density rho away from the background rho bar. Okay, so we want to think of rho check as being kind of order epsilon. Okay, or it at least to begin with, let's say. Okay, so if you do that, okay, so you just have a term like this, so that becomes dt of rho check. In here, we get some gradient like this. What you'll notice for the momentum equation, okay, so the momentum equation, I've got dt of u, right? So that now have a rho inverse over here, so that's why it comes to the other side of the equation. So I get a rho bar by dt of u check. I now get rid of my Burger's type term, okay, because it would be higher order in the perturbation. Okay, so we don't include that. But I still have some other terms involving the pressure and involving the gravitational potential. Okay, and so I get a term here also from the gravitational potential. Okay, so I've linearized the equations and I get this system here. And what we're going to do is we can actually combine these equations together. Okay, so in particular, if you take a time derivative of the first equation and you take an extra space derivative of the second equation and you combine it also with the third equation, okay, so just a bit of, calculus to manipulate these things, you will get the following equation that I've drawn at the top here. Okay, so what we have, okay, is a wave operator, okay, wave operator here with some parameter k. All right, so maybe just to say here, I've assumed that the pressure goes like k times the energy density. Okay, and then we've got a term coming from gravity. So this is just a simple ODE for the variable that we're trying to solve for. Let's say the perturbation in the energy density. Okay. And what we can do is, because we've got this wave operator, we can see, well, what happens, for example, if we looked at an ansatz where we assume that the energy density perturbation goes like a plane wave. Okay, so it's some linear combination of cosine and sine. Okay. If you make this ansatz in this equation, you will get the following dispersion relation, okay, which involves omega squared is equal to, I'm sorry, now I've got 2 types of k's. Okay, so I've got a wave number, bold face k, and I've got my speed of sound, capital K, minus something involving the gravitational perturbation. Okay, sorry, but minus a term which comes from gravity. Okay, Um, and so what we see, okay, what does this define? Right? We see that um, this this frequency omega here, okay, because we have this extra term coming from 4 pi g rho bar, this frequency can actually vanish. Okay, if we didn't have any gravity, right? If gravity were not switched on, we would not have this term. Okay, and so we would just have omega squared is equal to k times k squared, and so we would just get oscillatory solutions. Okay, that's all we'd have. Causes and sines, everything would oscillate. Everyone's happy. Okay, but because we have this extra term coming from the Poisson equation, coming from gravity, we actually now get what's called a critical length, which is called the gene scale. Okay, so this gene scale here looks like, you solve this, okay? Um, and what we see then is we see actually different types of dynamics. Okay, so in particular, if we're working at small scales, okay, which means K would be bigger than this critical genes length scale, okay, um, this would be a situation where I guess omega would be real, okay, and so we would actually still get oscillatory solutions, okay, things would go up and down. On the other hand, if we work at large scales, which ends up corresponding to small wave numbers, okay, in fact, here gravity would dominate. We would get an imaginary frequency omega, okay, and in fact, then the sign turns out to be the right way, okay, and you can show, okay, because you've got like an imaginary omega, the signs ends up being the way you want them to be for the imaginary part, and so you will actually see that the dominating solution here will be some exponential growth. Okay, so rho check here would grow exponentially. So this is called the genes instability. Okay, so it's this idea that you've got some homogeneous solution, and if you take perturbations at some particular frequency, you may get oscillations. Whereas if you take perturbations at another frequency, you would get growth. Okay, so the dynamics really depends on the frequency of the perturbations. Okay, this is the genes mechanism. So this was actually first done by Jean at kind of the early 1900s in the context of plasma, okay, plasma dynamics. And it turns out that it's also relevant in cosmology, okay, where we now basically transform these Euler-Poisson equations and see how do they behave on an expanding space. All right, so if we think before, we've been looking at physical coordinates, r and u, okay? What we can do now is we can now transform to co-moving coordinates x, okay? And we've got our peculiar velocity v, all right? And so we can transform the Euler-Poisson equations from before to this new system, to what will be a new system. Okay, so if you just do a transformation, r is like scale factor times x. You transform your nabla derivatives, your spatial derivatives, and you can also transform your time derivatives, okay, which again is just a bit of a chain rule. And what you get is the following system here in equation 1, right, where what you should notice now is we pick up lots of new terms involving the scale factor. A squared, okay? So if we're now looking at the system in co-moving coordinates, right, we get a lot of new terms here coming from the scale factor. And what we can do, okay, is the same analysis as just from before. We can say, all right, well, this system of equations, it admits an exact homogeneous solution, okay, which actually in this case will depend on time. Okay, so we might have some background energy density rho, okay, which as we've seen so far, should decay with the expansion A of t. Okay, so the solution, it's not an identically constant solution, but it's something that now just depends on time. Okay, you can work out for the pressure and phi bar and the scale factor A. Okay, so we have again an exact homogeneous solution, and so then we could say, all right, well, what happens to perturbations of that homogeneous background? Okay, and so once again, we do that linearization argument. Okay, so we drop terms which, as PD analysts, right, we drop things like V div V, which of course we're worried about because that should be driving shock formation. Okay, but what do we get? We get a system like this. So this is the top equation that I've drawn here. This comes from linearizing the continuity equation. Okay, and it turns out to be quite useful to write this equation in terms of a new variable called delta. Okay, so delta here is no longer just the perturbation of the energy density, okay, rho check, it's now rho check divided by the background. Okay, so rho check divided by rho bar. So this is so important. This is actually, this variable is called the fractional density contrast. Okay, so it's telling you if you have some kind of region where you might have an increase in density compared to what will be the background homogeneous state. Okay. So if we look at this equation here, we've got kind of two terms. We've got one term with which I've put here in square brackets, okay, which just involves the background rho bar, okay, and because this just involves the homogeneous background, that should actually just satisfy to zeroth order the continuity equation. And so in particular, this term here in square brackets would be zero, okay, and so actually we can simplify even this equation here to tell us that the time derivative of the fractional density contrast goes like a term like this. Okay. Now you can do the same thing for the momentum equation, okay, the Euler equation. So again, taking some time derivatives, I probably should have put checks here, okay, but we've got checks here as well. And then also for the Poisson equation. Okay, so again, looking at perturbations around this homogeneous and isotropic background, okay, and then just linearizing to first order. Okay, so if you do this and then you combine the equations, these ones here, these three equations, if you combine them together in the right way, okay, you get the following system here. And what do we notice about this? Okay, well, the first thing is we see that we've got a wave operator. Okay, we've got a dt squared here minus the Laplacian. Of course, the speed of sound here is modified by the scale factor A. Okay, but what do we pick up? We pick up a damping term. Okay, 2 times h. Okay, we're going to really interpret as a damping term. Okay, times dt of delta is equal to, again, something involving gravity on the right hand side. Okay, and so this damping term, what does it do? Okay, how does it affect the dynamics? What's going to happen? And again, I'm not going to actually write down the Jeans length here because it gets a bit complicated. But the idea is going to be that below a certain length, okay, so for wave numbers below a certain Jeans length, which is going to be large wavelength, okay, because this is wave number. But anyway, the oscillations are going to the dynamics, the perturbations of delta here, okay, they're going to oscillate, and then because of the damping term, they're just going to decrease in amplitude. Whereas on the other side, okay, when we look at perturbations above a particular critical scale, what will happen is actually the perturbations will grow, okay, just like we had in the previous case. But before we had exponential growth of those perturbations, okay, e to the something. And what happens now, actually, this damping term actually is going to damp that behavior, and we're going to end up with power law growth, not exponential growth. Okay, so a bit of a distinction there. Or a bit of a different behavior. Okay, so let me show you what I mean, okay, in the context of matter perturbations. Okay, so when I say matter here, I mean dust. So let's see what happens to the fractional density contrast of matter. Okay, and what we can do is we can study this equation in different epochs. So we can study it in the radiation dominated epoch, in the matter dominated epoch, and what we're in now, which is where we have a cosmological constant, okay, this other epoch. So let me just show you what we do here. So for example, in this matter dominated era, we know that the scale factor grows like t to the 2/3. So we wrote down before. Okay, and so we can substitute this expansion rate into this equation. I'm considering matter, so I know that the pressure term is 0, so K is 0. Simplify everything and tidy things up, and you will get the following ODE system here. Okay, and this admits 2 power law type solutions. Okay, one of them is what's called the decaying mode, and one of them is the growing mode. Okay, t to the 2/3. And what's really important, let's say in cosmology, is the fact that we have a growing mode solution. It's not exponentially growing, Okay, it's growing like a power law, and it's actually growing exactly at the same rate, t to the 2/3, as the scale factor. Okay, so in the matter-dominated era, we see that these perturbations, okay, are actually growing. And of course, in terms of structure formation, that's important, right? Because we're seeing that this fractional density contrast is growing, so we're seeing that matter is clumping together. This was in the matter-dominated era. Okay, you can also solve this in the radiation-dominated era, but for that, you don't want to be using Newtonian cosmology. You want to be using relativistic cosmology, okay, which is very nice. You can go through and do it. It's in that book by Weinberg that I mentioned as a reference, but not something that we've got time to do here. Okay, but we can also think what happened in the lambda-dominated era. Okay, so this is when our universe, this late time epoch where our universe is expanding like e to the lambda t. Okay, so again, we can see how does matter evolve in this epoch? Okay, perturbations of matter. So the equation that I had up here, okay, so again, I'm going to take k to be 0 because I'm just looking at matter. And I need to think, what does H do? Okay, H is A dot over A. Okay, and if we're living in a lambda-dominated era, okay, A of t roughly goes like e to the lambda t. Okay, so A dot over A is going to go like lambda. Okay, so this term here will be, I guess the physics argument is basically that this term here is going to be some constant, and for various reasons, I guess you could argue it's a lot bigger than the other term. You could even keep it and just do solve the ODE properly. Okay, and what do we get in terms of solving this ODE? Well, there's two solutions. Okay, one of the solutions ends up being a constant solution. And the other solution ends up being something that decays e to the minus 2 ht. Okay, so this is like a to the minus 2, okay, e to the minus 2 lambda t, something like that. Okay, and so how do we interpret this? How do cosmologists interpret this? It's telling them that when we end up in this later epoch, okay, this later epoch, this lambda-dominated epoch in our universe, the fractional density contrast of matter, it stops growing. Okay, so in fact, I guess you probably can even ignore this solution. I'm not entirely sure, but it really stops growing. Okay, so this is telling us that in this later epoch, we don't get structures forming. Okay, they're being suppressed by this. Well, we'll see. They're being suppressed by this quick expansion from lambda. Okay, so this is the gene's instability. Okay, so we see here that I haven't talked about the other case. I haven't talked about perturbations below the gene's length. Okay, but the fact that they oscillate, that's also important. But we've seen here that, you know, for certain types of perturbations, we get this growing solutions. Okay, and it's important that they are power law and not exponential. Okay, and it's in cosmology, it's very important the rates that you get. Okay, the fact that delta m grows like scale factor and all this kind of thing is something that is very relevant to them. Okay, so let me just have a couple of just very quickly, just a bit more cosmology, just to so you have a bit of a picture of what is happening. This idea of the gene's instability, it's something that is used to try and understand the density of different components in our universe. So what I'm showing here is kind of evolution in time. Okay, so as the scale factor is increasing in time, so going from something very small to order 1 today. And we may have some density of neutrinos, which is going to be like radiation, some density of photons, okay, density of baryons, all right. And so cosmologists, they as the scale factor has changed over time, they are trying to understand the rates of increase here and the rates of decrease and the rates of these densities, okay. And so one thing that you can do, okay, if you look at relativistic perturbation theory, okay, is you can study the behavior of not the matter component, but the radiation component, okay, so delta R. And so where would you want to do this? This is really relevant when we're thinking about the cosmic microwave background, okay, it's an emission of radiation, it's an emission of photons. and we'd like to understand perturbations of the photons, okay, of this homogeneous fluid of photons. We could say, well, what happens to perturbations of that? Okay. And so somehow the physics idea here is that you've got gravity that's pulling things together, okay, whereas we know that radiation is a fluid that has positive pressure, and so the pressure is pushing the radiation out also. And it's somehow the interaction of these two which causes what's called acoustic oscillations. Okay, so oscillations in the behavior of the fluid. And it's these oscillations which actually leave a very important imprint on the cosmic microwave background. Okay. Because at certain, when I say he waves froze, what I mean here is that for perturbations, let's say above the gene's length, the oscillations might just go back and forth, whereas for kind of smaller perturbations, we've seen that from the gene's instability, they might grow at some power law rate. Okay, so somehow all of this is giving us information. It's saying that perturbations of some size might give us this, perturbations another size might give us something else. And so this is what is very well studied in cosmology, okay, is the cosmologists will take the cosmic microwave background, okay, and they will look at the variations in the temperature. Okay, so as I've said, it's highly isotropic, but it's not exactly isotropic. Okay, so within here, if you're looking at different points, all right, there will be some small anisotropies. Okay, and so what you can do is you can take that function. Okay, so here it's a function on theta and phi. Okay, and how this temperature varies. And you can take that function and you can do basically a Fourier decomposition of that function. All right, which because it's a function on a sphere, it's going to mean we're going to decompose it in terms of spherical harmonics. Okay, so you might have some function here, okay, and you might want to decompose it in terms of normal Fourier modes, which of course is something that you can do. Okay, so the idea is we do this now, but on a sphere instead. Okay, so here we've got different spherical harmonics that you can decompose in terms of. Okay, and so that is something that is done, okay, for the cosmic microwave background, and that leads to this following graph here, which is called the power spectrum of the CMB. Okay, and so what it does is it plots the power of the temperature fluctuations, which is literally the amplitude, okay, and it plots it against the multipole moment of your spherical harmonic. Okay, so your spherical harmonic is indexed by two indices, L and M, okay, and you can take the sum over the M index, okay, and look at the value for each value of L. Okay, so if you do that, okay, you get this picture here, okay, and what we see is that there is some structure here. Okay, it's not completely random. And what we see is that we get peaks, okay, that come at certain points. Okay, and it turns out that these peaks, although it's probably not clear with what I've said so far, it turns out these peaks you can kind of very closely tie to the different densities of parameters that we've met up until this point. Okay, so for example, I think in particular the second and the third peak, okay, these are something that tells us what the initial density of matter components should be in our universe. Okay. And kind of the ratio between if we've got baryonic matter and dark matter. Okay, and so if you do kind of all this relativistic perturbation theory, you'll get these different parameters. They will predict the sizes of these different amplitudes, okay, in this spherical harmonic decomposition, okay, and this is what cosmologists then match to the data. Okay, so this is kind of the data that they see is what's shown in red. Okay, and the solution in green here, this is what the main model of cosmology, the lambda CDM model that I've presented you so far, that's actually what it predicts. Okay, so you just need to pick your parameters in this model to exactly map the data that we get here. Okay. And yeah, the fact that we're getting oscillations, okay, is coming from the fact that we're getting genes instabilities, we're getting certain oscillations at certain scales are being activated, leading to oscillations, and then we're measuring these oscillations via these spherical harmonics. Okay. So again, sorry, I realize it's a lot of physics, but I just think it's important to understand a bit what people do in cosmology. Again, just to emphasize, there is a lot of heuristics here. It's obviously a very complicated system because people are trying to describe our early universe, which is incredibly complicated, but there's a next to no PD understanding of these oscillations and this kind of behavior. Okay, it's something that really is still lacking. So what I want to do now, okay, is now for the rest of my lectures is talk a bit about some rigorous PD dynamics. And I don't have heaps of time left, so I'm just going to kind of very quickly start on this. I might end a few minutes late. Please forgive me. And then tomorrow I'll talk more about some rigorous PD dynamics. Um, and I think the thing to kind of keep in mind is that everything we've done so far in this genes and stability mechanism in particular is we set lots of terms like U, grad U, we set that to 0. Okay, whereas of course we know that if we were to study the Burgers equation and we were to set that term to 0, well then we'd have nothing to study. Okay, and so what's been done in the context of PD dynamics is actually putting this term back in and seeing what can we get. But it's certainly a question to ask is whether these, it's not clear to me even, is whether these kinds of shocks that you get are happening before the kinds of genes instability mechanisms are kicking off. Okay, the relationship between these two mechanisms is not understood. So let me just set the scene a little bit for what we'll now look at, okay, is seeing, okay, what happens when we put these terms back in, U, nabla U. And to get us going, it's useful to, let's say, look at one of the first papers that did this approach, okay, that considered this. And it's a paper by Brouwer, Rendell, and Royler. I think it's from about 2003, but I must say I didn't exactly check, early 2000s. So what these authors did, okay, is they took the Euler-Poisson system that we had before, okay, in an expanding universe. So if I come back just very quickly, I had this system of equations here, equation 1, okay, which was the Euler-Poisson system on some static expanding space, or maybe static's not the right word, but it's Newtonian, okay, so it's coupled in a different way to the matter, but it is expanding, okay. And instead of linearizing, which is what we did in the genes instability, the authors here have kept all the terms, okay, and done some kind of nonlinear PD arguments. So I wonder if I want to say something about that. Maybe not. So what they do, okay, is if we were to take this Euler-Poisson system, okay, on an expanding background, we can write down the PDEs, okay, and in this paper by Brouwer, Rendell, and Royler, they started off, actually in the paper, they talk about a polytropic equation of state. Oh, Max has said it's from the 90s. Sorry, okay, so it's a bit earlier. That's true, actually, yeah, 90s. Okay. So in this paper, they actually look at a polytropic equation of state for reasons to do with what was happening in fluid dynamics at that point. But what we can do is look at it for a dust equation of state. Okay, so if we take that system, okay, the Euler-Poisson in an expanding system, and we consider pressureless fluid, okay, so dust, then you can show that your PDEs take the following form here. Okay, so I've repackaged them slightly, but let's just see a couple of terms. Okay, so we've got the fluid equations I've packaged in a matrix system. Okay, so we now have a vector of unknowns V, which basically involves the energy density and the 3 velocity. All right. And coupled to that, we have the Poisson equation, okay, describing the gravitational potential phi with some scale factor a squared. Okay. And what is important to notice in the matrix coefficients that we get in this system, all right, so if we take them in term, okay, so we might have this matrix coefficient A, okay, and that just involves some of the fluid variables and rho minus rho bar, okay, so that's just, nothing so exciting. You do notice, though, that in here we're going to have terms which are like U grad U, okay, so the Burgers type term. What is very important, though, is we now pick up a new term, B times V. Okay, and what is this term B? This matrix here, it is exactly the scale factor H of T times a positive definite matrix. Okay, the matrix here is 2003. Okay, so something that's never zero. Okay, so what we will see is that within this system, okay, we've got hidden in this first part that I've just highlighted in yellow is going to be a Burgers type term that could drive blow up. Okay, but we also have now a term here, B, right, which is going to be the damping term, okay, which is going to prevent the blow up from occurring. Okay, and of course we also have in here an additional term, P, and this is just coming from the gravitational potential. Okay, so maybe just very schematically, okay, we're just looking at equations of this type. Again, it's going to be this extra term B, this damping term, which is going to prevent this system from degenerating in finite time. Okay, and so that's actually just what I'll end on, which was just to remind you how this phenomena even occurs for damped ODEs. Okay, so if we think about the Riccati equation, phi dot is equal to phi squared, okay, well, we know that this can be explicitly solved by the equation that I've written here, okay, phi naught divided by 1 minus t phi naught. And so, of course, even if phi naught is very, very small, the initial data is very, very small, we can still get finite time blow up. Okay, the solution will still blow up in finite time because this denominator will still tend to zero. Okay. But if you add a damping term in, that dynamics completely changes. Okay, so in particular, if we take that Riccati term and we now add in a damping term, which I write here as minus d times phi, okay, where d is some positive number, then again, you can explicitly solve this ODE and you get something like this, okay? And again, sorry, not again. Now the dynamics are quite different, okay? So you can set things up, okay? So D, you could set D to be 1. As long as phi naught is sufficiently small, okay, you can guarantee that this denominator here will never go to 0. Okay, so this damping term here prevents you reaching that finite time blow up. Okay, and so exactly this kind of heuristic, okay, is what's going to happen in this system of equations here, okay, where we have a Burgers type term hidden in here, which could drive the blow up, but actually it's going to be this additional term in green, okay, which is going to damp the system and is going to prevent that blow up from happening. Okay, so that's the kind of nonlinear dynamics that we're now going to study, but I think that's a good place to stop. And yeah, I'll carry on tomorrow. So thank you all very much for your attention.
So thanks for the wonderful lecture, Zoe. Are there any, we had a few questions during the lecture, but any other questions? All right, well, if not, then we'll break for lunch and I guess you
Mhm.
can go out and play in the snow if you're into that.
Yeah, exactly. Yeah.
Or stay inside and do math and physics.